pressing. Okay, we are live, I guess. Hello, everyone. This is Nick and Ilya with me, my co-host. Hello, Ilya. And this is the first episode of season 2 of Postgres TV YouTube show, fully about Postgres. And we have a very special guest today, Michael Freedman from Timescale. Hello, Mike.
Hi, thanks for having me.
Thank you for coming. This is very long-awaited event. So we discussed it started to discuss it 3 months ago or so, but eventually you are here, so we are very happy to have you here. So Ilya, you wanted to ask the first question about?
I always want to ask the first question, and we run out of time. Nikolai usually starts to ask the questions. It's usually like this. So basically, I think many people read our file with small introductions of who you are, and probably TimescaleDB doesn't need of much introductions currently, so many people already knew what it is. And the historical question which we usually ask in the first row in this case would be like, why TimescaleDB? How did you come to it? What was the motivation? Was not enough in current database landscape to start making TimescaleDB?
Yeah, no, it's a great question. So, I think it started about, really about 5 years ago. And my co-founder and I, Ajay, we were kind of both at our stages of our careers where we wanted to kind of take the next adventure, and thinking about, what big kind of almost tectonic shifts we were seeing in the industry was, kind of the last 30 years was all about the digitization of the back office. Like IT was like, it used to be things that are done on paper, now being done in on computers. And I think what we saw was that the same thing was happening with what some people call OT, operational, technology. And this is really kind of like, what some people think of maybe as industrial IoT or logistics. It's that, everything's being digitized. And so when we started thinking about, what this type of thing needed, a big part of it was that they were just putting off, all these sensors were putting off more and more data. And we were starting to think about like, what type of platforms would you want to enable you to kind of collect, store, and analyze that data? So we started basically building, what was a SaaS platform for IoT data. And, of course, one big part of it, in addition to libraries to collect it and to analyze it, is you need a place to store it. And so you do that with a database. And so we started using what were some of the open source offers there, and really just weren't pleased with what was available. And in particular, most of the existing kind of time series databases were NoSQL, and they were usually pretty limited, because I think most of them came out of the kind of observability space where you're like, well, you have tags and you have floats and you don't have any other type of data. And so the way we deployed it, and the fact is for many of them, these are actually the recommended architecture, is you deploy your time series database, and separate from it, you deploy another database like Postgres, or some people use Mongo, to store all your metadata. And if you ever want to ask questions like, look at certain devices based on their type, you actually need to do these type of joins in application space. And, we're like, at some point we realized we want to do certain types of queries. And we were at that point frustrated with performance, with, the ability to do high cardinality, which is how many so-called distinct tags you have, like distincts. The query language, it's SQL-ish, but, it often lacks a lot of what you want. The reliability, some people say it takes good 10 years to build a reliable database. And it's not because, look, it's kind of easy to do, not easy, but like, it doesn't take you a huge amount of time to do some low-level hacking to make a scan look fast. But when you want the entire ecosystem, when you want it, to do proper recovery if you fail in the middle of recovery, all those things which just take maturity, it takes a long time. So, but we were sitting there looking at this database, and we wanted to ask a question about a type, and we realized that we need to do a 4-week engineering sprint to do what should just be a join. what should just be a SQL join, because we need to, write this code in application space. We had to version the application code. We had to do rollouts. We had to do this. And we stepped back and said, there must be a better way.
Types of joins, optimizer,
yeah,
and things like this.
And we thought there must be a better way. And so I think that really led us down the path to thinking like, what is it about time series workloads that is different from traditional, relational workloads, OLTP workloads, or frankly, even like, the traditional data warehousing, like, TPCH workloads, where you might want to design yourself architecture a little differently. And if you design around that notion of time series data, that most things are inserts, they're not updates. Most of the thing you're inserting for, the latest time intervals, but not solely. Queries are often shallow and wide in that you're asking about many things over a fixed time period, or deep and narrow in that you like pick off let's say a device ID or a stock ticker, and you want to do long scans of them. There's architectural decisions on how you organize your data that you could then optimize for that. And that led us down the path of like, we loved Postgres. We really, wanted a reliable database, battle tested, wanted that support for SQL, wanted all that, the ecosystem and growth, and had experience using Postgres internally. In fact, some of the team had experience like, building on top of it, both with extensions and with PLPG SQL. And so, that led us down the path of thinking about how do we, basically make Postgres into a time series database. And what was really important from us in the beginning was that we want to organize it as an extension, not a fork, because that allows us to play much more with the community. And as Postgres continues to evolve, kind of, Timescale could continue to get better, benefit from it. But we also saw historically how every database that forks, I mean, in previous years, whenever you're like writing a Linux kernel patch is a disaster, because you realize like every version you spend 80% of your effort, caching it up. And the same with most of the Postgres forks, that they don't age well. So, it was really exciting to see the work that the Postgres community did, over the last, 10 or 15 years to build this type of extension framework, that, perhaps where it started, it was people, introducing a new index type or something. But I think it really is a testament to the careful engineering that was done over time that allowed people to build as much as we did.
A short question, sorry for interrupt, because you mentioned that. Extensibility is a very interesting feature of Postgres, and many people like selling Postgres because it's very extensible and there are extensions, you can write new indexes and so on. But many people actually are complaining that this mechanism is not quite good. It's a bit not up to date. It has some flaws, etc., etc. So basically, making Timescale, you probably was busy with Postgres extensions and extensibility like a few people. What is your opinion on that? Is it good? Is it bad? Does it need something to be improved?
Yeah, we have a close question. What do you miss in Postgres extensibility features? Like, what would you like to have in Timescale but cannot build because if it's on top of Postgres?
It's a very important topic for the community because it's like,
Yeah, no, it's true, and it's it's one of those things where like many great pieces of software, like the journey is never over. So I want to first caveat my statement by saying, like, I think, there's always new directions that you want to take software in, and sometimes where people haven't thought about it before. So, I leave this, I want to talk about some of the things we found, and, just want to, be clear that these are absolutely not criticisms, but just like, as people continue to push technology new ways, you want to, you need to, it's helpful to have a, constant evolution. So let me talk about some areas. So, first of all, the fact that we have hooks throughout the system turned out to be very useful. And, we are, we're able to, I think, engineer a lot of things that people didn't expect. I think one great example was the way we introduced native compression, in the sense that, many, often you think, well, if you need a compressed storage layer, you need to rewrite the entire storage layer from scratch. I think there are interesting things, the way that, the table access methods are developing. And I think there's stuff that we're starting to look into to think about, how, if we think about the continued extensibility with Postgres as it started to innovate really even at the storage layer, I think opens up new possibilities that we are excited about and hope to explore and hope to contribute more on. But I think it also means that sometimes, limitations make engineers creative. And so it was pretty interesting in the way that we effectively kind of built what looks like columnar storage by carefully thinking about, packing data into arrays in toasted tables using kind of like custom compression algorithms based on the type you have. And yet, so we're almost able to reuse kind of what is row-based storage underneath, but it's actually doing like columnar projections into them. So I say that because there's always things that you can make better, but you could also sometimes reuse things in unexpected ways to get like, almost as good or sometimes even better results than things that are built natively. And I think that's been a fun part of the engineering. Back to your question, what are some places that we found that could, let's say, maybe that could lead to further work in the future? I think one of the part is really, and I know this sounds like a not obvious front and center thing, but turned out to be a heavy lift, was actually version management, in the sense that
updates of extensions.
Yeah, updates. And, it was really built around the model that like most extensions are going to be like, is like a function. And, when we talk to the team, because, for example, a PG dump doesn't carry versioning information, as an example.
PG upgrade cares, but very interesting.
But that's usually for more major upgrades than, and similarly, an extension installs into a database, not the cluster, not the whole instance, which means that actually in a single Postgres instance, you could actually have 6 different versions of Timescale running. And so if you think about it, like, well, if the difference between version to version is pretty trivial, it's maybe just PLPG SQL, who cares? But most of the time you think about installing a single .so file, and we're making low-level, integrated at the C level with the planner. And so this notion of like, well, every version should be perfectly backward compatible doesn't work when you're integrating at the level which we are. So for example, the way we needed to do this was actually that our versions, we built basically a separate stub loader that basically loads multiple versions of Timescale into a running Postgres cluster. So at any time, you could actually have different .sos that are running in the same Postgres instance. And then these are being basically, like, the loader is loading it at the alter extension time. And so our binaries, if you look at our Docker containers and when we deploy in the cloud, they're actually deploying with multiple versions of Timescale. And you could say, well, maybe the answer is just don't have people run different versions across different databases. But it turns out that if you want to support upgrades, because installing the SO is a distinct element from running alter table, you actually need to support this anyway. So there's a lot of upfront stuff that was really, what I would say, this is something that's more infrastructure. This is not benefiting Timescale per se, but this is really infrastructure work we need to really do, given the level, the aggressive level to which Timescale is an extension compared to a lot of others.
This is interesting mechanism. Did you consider contributing to Postgres to improve it in Postgres itself in core?
We brought this up. I mean, obviously, one thing that's different is as a startup, we're operating at a different cadence than Postgres is. Major versions are released once a year, and this is a non-trivial case, and there would often be several years.
It'll take several years.
Yes. Take that. I mean, we did bring this up in some mailing lists and talked about what we did, and I think there's this general. It is a lot of complexity, right? And the general sense of like we're one of the few extensions that need this, but I think that's really the size of how we call it aggressive an extension we are compared to a lot. And so Postgres is, I think for good reason, there's this tension between stability and innovation. And again, when you try to innovate, you're often asking, how many people does this impact versus the the potential complexity of solutions. It's honestly not something that we aggressively try to upstream. As when we were smaller then, and we had other priorities. But we've actually just started recently hiring people whose sole job is whose main job is to actually be upstream contributors, and we are looking to contribute more in that layer, more in that end. So we're going to start thinking about more on how we could try to work with both be good citizens, do PR reviews and help with commit fests, but also how we could start trying to upstream stuff that we think would benefit others as well.
Yeah, this is awesome. So I have a lot of questions, but before that, I want to remind that for our online viewers, you can ask questions in YouTube chat. We monitor it, so we will deliver your question to Mike. And
let me add just one last question before you go on. So that was a lot of infrastructure. There's clearly stuff, I think, the more hooks we can get around planners, the more we can interact with optimizers. The stuff with storage extensions and the table access methods are all really interesting to us. And I think we're gonna continue to explore what we're doing. And then I think we have a bunch of questions about multi-node. And there we even took it in a very different direction, which is, we are building a lot more on top of it. That's kind of doesn't align exactly with existing primary backup replication as traditional to most databases, that we're doing a much more horizontal scale out.
This is whole area. I'm going to return to it a little bit later.
Cool.
Before that, I also posted linked, speaking of compression of time series, a great article in Timescale blog. I will repeat it in comments later. So this is like I like this article a lot. I recommend everyone to read it. Like it's interesting, really. And also looks like this, like your approach, like there are two camps, and like over a decade ago, Michael Stonebreaker said like one size fits all. The idea, like one universal database for everything. This idea was in the past like measure one, but the time has gone. But right now, Michael Stonebreaker is blogging in EDB blog, like against MongoDB, against DynamoDB, defending Postgres as a universal database. And looks like you're definitely in this camp, like really one size fits all. You can have some universal database for everything. What do you think, like conceptually, like on high level?
Yeah, I mean, I don't know. I mean, I think I always view Timescale as we are really focused on time series and what I would call real-time analytical workloads. And so, you mentioned, or Ilya mentioned about, Postgres, one of its things from day one when it started at Berkeley was about extensibility. And, obviously, Stonebreaker over his career has recently got into, and a lot of, I mean, some of I'm also an academic, and that they've done great things with columnar databases, with what was CStore and became Vertica, and he later did kind of databases for machine learning. I think those are, and I think one of the ways to think about it is, are there core aspects of your database that you could reuse, and yet somehow think about specializing them for particular use cases and workloads? And I kind of view that as what we did in Timescale, in that you start with this great basis of Postgres, and then we think about how to kind of massage it and do a bunch of optimizations and do a bunch of changes to make it work for us, while we could retain basically we make architectural decisions that, don't let you retain 100% of the functionality of Postgres, but let you retain, let's say, 99% of the function. And those trade-offs that we make are intentional in that they're kind of architectural in nature, as opposed to when you try to build a database from scratch, you don't support a lot of things, just because it takes 20 years to do that. And we've kind of gone from the other direction, where we start with Postgres, and then sometimes we need to drop support for certain things because of architectural decisions where we might do for scalability, let's say.
Do you have some examples? What kind
of?
So
for example, one case right now is that we, from the beginning, we only support unique indexes or unique keys that are include as part of them the partitioning key. And think about, we say you partition on time, or in multi-node you might partition on time and space. If you want to define something as unique constraint or like a primary key, that primary key has to include, that is, if it's composite, it has to include the partitioning keys.
If you have, for example, ORM like Ruby on Rails, and which tend to use surrogate keys like numerical ID.
Yeah. So one of the biggest integration problems with ORMs is many of them assume basically an auto increment primary key, like that's just a number. But if you start thinking about a time series workload, like where does that appear? And most of the time, when people are using like ORMs for these time series workloads, they're actually trying not to use that approach of primary key, because it's not it doesn't really, it's not sensible. Typically, let's say a constraint would be if you're, let's take a user analytics case. Maybe you define a unique key on user ID and a timestamp. So each user ID could emit one event per timestamp, which again is in microseconds. Or maybe you don't have one at all, because most of the time you don't need uniqueness. That is very expressible in Timescale and what we support. But I think that's especially true when we start getting into multi-node, where again, supporting a unique auto increment key is actually a distributed consensus problem, and is therefore a huge scalability limitation. So if you look at most scale out databases, they have limited support for those type of global auto increment IDs anyway.
Makes sense.
Per se, it's just not easy to implement, especially if you have that amount of data you need to scale out.
Yeah, it's not easy to implement, but it's partially fundamental because it actually requires agreement on that global, that global ID. And so that would basically become then, if you have a distributed database, that would basically become a service that sets out those auto. Yeah, I mean, you could do it. It definitely introduces fundamental scalability limitations. And so that's the decision of why we chose not to allow it. Because again, we don't think it's actually useful for our use. It's that useful for our use case.
Yeah. If we consider, I have like a question somewhere in the list. If you consider some like social media basic database schema with users, groups, I don't know, like blog posts or posts and comments, what part of database could fit Timescale like naturally, efficiently, and so on? I can assume like if you have some audit log or newsfeed which has like very close to, like time is very in the center of data. It's of course naturally goes to Timescale, but what about comments, posts? I don't know, users maybe.
Yeah, so I think I think one of the things we like to say is that we kind of think that almost all data is time series data. That when you store at the highest fidelity.
Very, very interesting. I read about it like a couple of months ago. I constantly thinking about it. I'm not 100% convinced, but it's like it's provocative statement. But
yeah, I mean, like the funny thing is like, time series data. I mean, event sourcing is a form of time series data. You're capturing the change of your state marked by timestamp, right? And in some sense, your wall is doing that, right? But I mean, back to your case about the social media. I mean, I think there's two different ways to look at this. Like, what is the application? What is the use case you're trying to do? Like, if you basically are building what is a lookup cache where you want to look up, users and just the current state, that's, maybe that doesn't fit. But if you're trying to ask the question about like, can I get a temporal view of like, what is the list of all posts, and that you ask questions like for a topic or even latest posts, right? It very much does support it in the sense that like, every post has a timestamp and it could have a UUID, could have a user ID. Those are foreign keys. We support those type of things. And you could ask questions like, get a list of, you could slice and dice in a different way. Giving the timeline of a certain user. It's, select by user over time. You can get the timeline of a region, like, tell me all posts about this topic, all posts within the United States. So there's various different ways where you could explore this state in a time-centric world. Now you're talking about Facebook, so you're talking about a system that's doing, I don't know, hundreds of millions of things a second. There's obviously lots of engineering trade-offs you're going to do for that. But I think that we've had people who, let's say, who are building a much smaller version of Facebook or of social media or whatever, that very much use Timescale.
I think every good developer should do it. Backend developer should do it at least once in life. So, but okay, this approach is like makes sense, 100% sense to me. So it's like workload oriented. Think about your workload and understand. But what about like, for example, comments? Okay, posts. We have we need to select like latest for user. Okay, maybe Timescale is a fit, but what about if we need to support a lot of updates? So my concern is
correct. So I think there's two parts of this, and one is when I say all data is time series, what we mean by that is that the finest granularity you could store your data at is in the notion of recording the change, not doing the update in place. So for example, if you do updates, I should say that Timescale absolutely supports updates. You could update old data, you could delete old data. The structure of it is just, it's slightly less performant. And when I say slightly less performant, we're not talking about like, we're somehow doing a couple of seconds. What we're saying is that the way we structure it, what we really do to aim is to really keep the working set of your recent data in memory. And so if you're updating old data as opposed to recent data, it's more likely then to just have to pull it from disk. And so when we say like less efficient, we mean that for really old data, when you're updating it, you're probably going to have to read it from disk rather than it already being cached in memory. Of course, that's true about any database effectively, unless you're want to just throw memory at your problem. When you have a lot of data, if you're doing random updates, you're often going to eventually need to pull from disk. Yes, there's some changes, but we don't have to go into them. But going back to this question about like, what is the workload? Like an alternative way to store the update is actually to store it as a record of like an update record rather than do it in place. Why that's useful? Well, often when you look at applications, if you want to do a track changes, what track changes allowing you to do is to see the history of the changes to your state over time, as opposed to just storing the latest version of it. So I would say, again, this is application needs. Storing it in a more, you could do updates in place with Timescale, but storing it in a more kind of time series centric world allows you to always basically keep the latest state and therefore then track the history of your information over time.
Yeah, we all know the flows of this because of MVCC, how it is implemented in Postgres. So what in this regard, is it a good strategy from perspective of your long-living system to keep update records instead of updates in place?
Yeah, I mean, when I'm talking about, I mean, yes, the parallel, of course, is MVCC where you're, versioning it or whatever. I mean, when I talk about updates here, I'm actually more referring to it from like the application perspective. You could, kind of Nick asked, like, for these workloads, what about updating? And I said, yes, you could store updates in Timescale. But if your application wants to actually, track them as individual kind of changes of your state, so we could expose this to the application, that's in some sense an alternate way to do it that also feels very time series centric.
Actually, I'm afraid I can just drop a bit too deep into the computer science part, but I feel your interest in this regard. So basically, classical databases like Postgres, they always trying to solve primarily the task of serialization of data. That timestamp ordering approach, timestamp inventory sort of data, does it contradicts with this concept or not? So basically, doesn't maybe have some troubles to build this time series thing on top of the Postgres, which is like designed to serialize things, maybe to linearize at some point?
I don't think so. I mean, from maybe the challenge of this, the complexity in this discussion is we're jumping between two levels of abstraction. One is what is exposing to the user, and one is, what do these mean semantically at the database layer? From the database perspective, you're storing, records, and, commonly in Timescale, one of the tuples in that record is a timestamp. From the database perspective, again, an update is just, an MVCC update to a record, and it has a timestamp and an old value and a new value. The thing I've been talking about, to Nick's question about, do you want to, store your change as an in-place update? And by in-place update, I mean like call update on your database that's doing MVCC. But as an in-place update, or do you want to store a new record, is kind of depends on your application. I mean, I'll give you another example. So for a lot of financial applications, you want to store your knowledge at a certain time. And then if this ever changes, you don't want to overwrite it. You just want to store another record that says, my knowledge of the system is this, and my knowledge is at this time. Because you kind of want to, again, this is time series idea, like, what did you know on January 1st and what did you know on February 1st? And so it's important just that you store both knowledges of what you have. That's kind of
like a lot of knowledge.
And that's kind of like, those are the application level view, as opposed to, this is not talking about, low level stuff.
If we have purely this like append only workload, what is, like, we have a question in our YouTube chat, which is better, Timescale or ClickHouse?
So there's a lot of meta questions there. Again, append only. So I think the important characterization is, one, we actually don't, one thing we see again and again is that time series workloads and append is a funny word because they are insert mostly. And so they are neither insert only, and they are also not append only. And at least my distinction between insert and appends is, typically when I think of appends, I think of a log, and the append is you're always writing to the last point in the log, right? The blockchain is append only, modulo the latest forks, right? The difference is when you're doing inserts, any real workloads, most of the time you're inserting to recent, but they're all a little bit out of order, right? You have data coming from different places with different timestamps, and you certainly don't want to have to serialize accounts.
Good example, sequence in the database.
You don't want to have to sequence the database before you insert it. And so there are some databases that do that, but I think that they then suffer ingest rates because they have to queue a bunch of stuff to sequence it, and then they generally have limited ability to support out of order data. And again, when I say insert mostly, and you asked about updates, I think many things are recent, but it's really common to have to go to backfill. Sometimes, insert stuff historical, missing records that you want to insert later. Sometimes your data has mistakes and you want to correct it. We see this a lot. It's really easy to corrupt your databases in IoT when you have some clocks that are out of sync, and all of a sudden they start telling you that the clock is 1970, right? You want to be able to correct those things or throw that data out, because all it's doing is messing up the rest of your analysis. So, we haven't done that deep a dive on ClickHouse yet. We hear, good things about its, some things like its scan capabilities. But, it does come with, I think, my understanding is a lot more kind of limitations around updates, around deletes, around updates, about kind of, you need to do much more manual sharding and management across the different nodes. And I think if you look at multi-node timescale, that's much more transparent to the application.
So it's much more append only than
much more that, much more append only, kind of much more manual. I think one thing from the beginning that was really important to Timescale was to focus on the developer experience. And so I think over time, in many cases, we do offer, really compelling performance. Like the compression, I think, is very compelling. On average, we're seeing 94 to 97% compression, which is pretty amazing. but really also to focus on ease of use to give people that kind of Postgres experience that they want and love.
Mm-hmm. And as I know, the recent version 2.3, like inserts can be you can insert into compressed chunk, right? So it makes like everything you just described like connected. Like you can insert to old chunk, right?
Yeah. Mm-hmm. So it's one of those things where you want to I talked about updates. You could always update to old data. When we introduce compression, the compression, and one of the reasons we don't have compression default on, because right now our compression, when you had a compressed chunk, is immutable, which would lead to usability limitations. So right now you turn compression on again, generally with most writes to the latest time. Our general approach is you configure this, your last hour of data, your last day of data, your last week of data is uncompressed. And then as data ages, we've built a background scheduler into Timescale that we use for a bunch of things, including these internal tasks. And it's actually user facing. We have a framework we call actions. You basically have an in-database scheduler where you could build your own stuff too. We'll compress your chunks as they age. And from the beginning, we know that obviously making them immutable was a limitation, but we wanted to get that, allow users to start using us and improve it over time. And so last month, which was pretty cool, we had the first thing where you could write directly into a compressed chunk. But again, the naive implementation is every time you do a write, you try to decompress, the compressed column, insert it, then recompress it. That would cause your insert rate to really go down when you're at least backfilling. And so that's why we didn't do the naive thing from the start. But what we did was we kind of did is really, I think, some nice engineering by our team, where when you insert into a compressed chunk, it would actually almost insert that as a separate compressed tuple, and the planner or the execution nodes would be smart enough to know that for a given key, it could be in this special intermediate table of compressed values or the final compressed value. So again, when you're querying it, you don't see any of this as the user. It just looks like it's one big table. You don't know any of this. But when you insert into it, it writes in these individual tuple by tuple compressed. And then again, we use our background scheduler to asynchronously take these updates, batch them, and then merge them into the total compressed chunk as one kind of larger action.
By the way, this process is like it's a single process, single threaded, right? I mean, you cannot control how many cores it will use.
So we there's a couple. Yeah. So our background scheduler, the background scheduler can do many things, many jobs at once. Certain tasks do take certain amount of locks. And some of those locks are fundamental. Some of those are implementation details. I believe currently you could only have one compression task running at a time. I don't think that's fundamental in the sense that I think the slightly better version would be one task running on each chunk at a time. This is just something where, again, this type of lock discipline was easier to implement at that time, and we'll improve it over time.
Okay, interesting. Yeah, I played with myself and I've noticed that there is only one process which took many hours because I had billions of rows and so to compress also. Right. Okay. Interesting. I have a bunch of very simple questions. Like for example, how big is the largest timescale database?
Yeah. So that's the funny thing. That's the funny thing about open source database, open source projects, or community projects. You don't always know what's out there.
But you have tracking enabled by default, right? So
we do have telemetry.
Long time ago, I think it was improved.
We do have telemetry. What we find is that some of our most corporate users turn telemetry off. So of course there's that. But we for multi-node Timescale, we certainly know of users in production. Actually, a really big company, building kind of analytics for live video streaming, and I know that they have about 2 separate clusters, each running 25 servers. Kind of so that they're getting to some real scale. Do definitely have things in the hundreds of terabytes starting to approach kind of a petabyte scale. Individual single node, I think, easily we have had 500 billion rows in a single database. With the new compression, it's certainly feasible to even reach 1 trillion rows. I don't recall if we've tried reloading experience, but unfortunately loading 1 trillion rows in a database takes so long that we get bored of it. Yeah.
All right. Several questions here also. So you mentioned this like 25 servers. Is it sharded timescale or
that's what we call multi-node.
Multi-node, okay.
The terminology is funny because
why not sharding? You try to invent terms everywhere, like chunks instead of partitions.
Well, I think often, the reason we don't try to create confusion, but I think what happens is that there is different communities have different terms, and there's often mismatch. So, for example, cluster in Postgres world means 3 things. A single instance is a cluster because back in the old days you did run them, and so you look at a single server and call it a cluster. Postgres terminology. Most developers don't think that way, but Postgres, like most traditional RDBMS, also has primary replica, and so a cluster is often a primary replica, primary backup replication. And so when you use the word clustering or a distributed database, to some people that means single node, that means primary backup, and that means what we call sharded or multi-node. The reason we didn't like the term
SQL command cluster. So
yeah, and the reason we didn't like the term sharding is because sharding, if you look at like the MySQL world or like a lot of the traditional world, it is shared nothing, where it's an application level thing. You take a database that doesn't support operations between them. In application level, you just split the workloads, and then you do sharding that way. The other thing is that timescales like chunking is much finer granularity than when you talk about most so-called sharding. In most sharding, you take a traditional ID space, let's say a user ID, and you basically create these fixed shards. And that set of nodes always gets mapped to one, and this set always gets mapped to another one. You do it by hashing, you do it by some consistent hashing. This is how most NoSQL databases work, right? The difference is that actually the way our chunks work is that there's not a fixed, there's a lot of flexibility in that a particular key space in what we call the space partition can actually reside on different nodes over time. And actually, that's a big part of our elasticity, in that in a traditional system, when you add a new node, what you need to do is you actually need to move a partition from one server onto the new servers in order to use it. You don't need to do that with Timescale. And that's actually pretty powerful because typically adding a new node would cause a lot of data movement in a cluster. Whenever you start moving data between databases, ops people get really nervous because you can lose data, right? And with Timescale, when you add a new server, the only thing it needs to own is a particular chunk. And that chunk is defined almost in this like tiling in time and space. So which means you could add a new server and you actually don't need to use it at all until the next chunk gets created. Or you could start using it for the new chunks and you asynchronously get a copy over the old chunks. But the thing is that our planner is smart enough to know where a chunk resides over time and space. And so elasticity becomes actually a lot simpler and also in some sense a lot safer because it doesn't necessitate you start doing a lot of data movement in order to incorporate this new node. And so I think, the terms have meaning to people. And so sharding often meant something very specific to people. And that's why we were trying to think about a word that doesn't lead to people having wrong conclusions.
Mm-hmm. And what about in your case? What about high availability properties? Like if we, for example, in regular sharding, if you lose some shard, only these users are affected, and others users continue. Everything is operating normally. But what about Timescale? If we lose one node or two nodes, what happens?
Well, I think there's two different questions there. One is if you lose a node, you can still do reads or writes to data that resides on other nodes, right? That's not affected. But the bigger thing is that obviously we want it so that you could lose a node and nothing's affected. I think there's two answers to this. I could talk about what we're doing in the database, and I also could talk more, we also build a cloud platform, and I could talk about how we're doing some more cloud native
Both
things.
are interesting, but we don't have a lot of time.
Yeah.
So maybe
I think the short answer is the database, the multi-node database has a notion of a replication factor, so that whenever you write a piece of data, a chunk actually resides on, this is not using Postgres mechanisms at all. It's using kind of distributed system stuff that we built on top of it. So it will do a two-phase commit to write this data to multiple nodes. And then, so if you lose a node, it could still be available. Now, the version we've released already does this two-phase commit. You could define replication factors. The current version that's kind of GA does not yet support moving, after you have an individual failure and bring another node back on, re-replicating some of that data, or automatically failing over from one copy of the data to another one. That's stuff that's very much actively being developed right now, and we expect to release in the next couple of releases.
Also, access node, it also needs to be covered by like some replicas, right? Because it also can fail. Access node.
Yeah. So correct. I mean, I think in the short term, we plan to take, that is one place we plan to use, more of Postgres physical replication to support. I think longer term, we could think about doing other things there.
Interesting about cloud. Like, can you describe what kind of pieces of software you used to building it? Or like,
yeah, so
did you use Kubernetes at all or no?
Yeah, we've kind of gone all in on kind of Kubernetes and various cloud native technologies. I think that one of the big parts of this was allow us to decouple compute and storage. So we're using kind of cloud network remote disk and replicated disk for higher availability. I think the great aspect of that is, and even if our cloud today, you could independently scale compute and storage. In fact, you could take a running database and go to the cloud UI and slide up, hey, I want to jump from 20 gigs to 5 terabytes, and you have zero downtime when doing so. And it really allows users to have that level of control and really make them, allow them to make decisions about what they actually need and how that affects their costs. The other great part of that is you basically get HA for free. And so in a traditional, when you have a primary replica, you're paying twice as much. You're running 2 servers, somebody has to pay for it. So, you're going to pay twice as much. Here, the storage is replicated multiple times and it's relatively inexpensive. But if your server ever crashes, either Postgres crashes or, full hardware failure, the platform is continuously monitoring the liveness of these, compute nodes. And if it fails, it immediately spins a new one up. And within, 20 to 60 seconds, you're up and running, not having lost any, reconnecting to your existing storage, not having lost any transactions. So you basically get kind of HA for free, which is a pretty powerful thing, I think.
And this works.
I have actually a related question. So basically, when we are talking about normal PostgreSQL installations, we usually have some sort of good approach. So basically, like most of the people, I think so, are using like PG bounds in front of Postgres. Like many people using Log or PG backrest to back it up, and so on and so on. We have some generic recommendations what we definitely need to change in PostgreSQL conf. Are there some specific recipes for Timescale? What is better for Timescale? Which other part of the ecosystem?
A special tool, I know. There is a special automatic configuration tool shipped.
I mean, we have a tuning tool that, I mean, the short answer is if you obviously use our cloud, we do all this stuff for you, so you don't think about it, including incremental backups and all that stuff. But yeah, we have an open source. It's a tune tool. It actually comes in our Docker container. So if you run our Docker container, it auto tunes itself. And so yeah, there are a bunch of settings that have to do with the fact that it's an analytical workload. I don't recall, it's setting shared memory, it's setting shared buffers, work memory. A big one is make sure you have enough locks because of all the chunks need a separate lock per chunk. So playing with that. One of, again, the cool things, I was talking about a cloud when I talked about resizing it, is again, when you resize it, you realize if you increase compute or memory or disk, you probably want a different setting. And so actually with our cloud platform, if the service ever changes size, changes compute, changes memory, changes disk, actually behind the scenes, we're auto retuning your system for you. And so again, there's lots of stuff you can do. And I think part of at least being what a managed service means is to hide that complexity from the users while giving you access to these things. If you want to, tune them manually, you can do that as well.
We have a question in chat. Timescale doesn't use Postgres built-in replication, so you can use it, right? I can answer.
Absolutely.
You can use it,
yeah,
but
absolutely.
in cloud, you decided not to use it. This is interesting.
Well, I think there's two parts. We will probably introduce the ability to do things like read-only replicas and stuff.
It's like RDS, right? They also have.
Yeah, you have it. I think the answer is that for many users, some people need that, and we'll have that available. And we have a version of our cloud which actually supports that today, and you could spin up traditional replications and read-only replicas, as many as you want. So we actually do offer that if that's what you need. For a lot of users, it's not worth the 2x the price, right? And so they want HA. I mean, I think it's a great example when you want to use your replicas for scaling reads, right? And you don't want to necessarily need to go to the multi-node, which is an alternate way to do it. But if your data fits on one node and you need to scale reads, I think having a replicas are great and a great solution. If all you're using is for HA, it's not. I mean, there are some workloads where having that 30-second downtime for that rare crash is unacceptable. In which case, it's those work. I think for a lot of users, they're willing to get half the price and introduce if that means that their failover will move from 10 seconds to 30 seconds or a minute, that trade-off is worth half the price for them.
Right. Interesting. Very high level and a little bit tough question. So you started with the idea that let's use existing good SQL database system, Postgres, and build on top of it very good time series system. But outcome, good outcome for users is that everything is in one place. You don't need to split data and deal with split databases, but
siloed like time series plus
right, exactly. But in case of, if we talk about cloud, you provide good cloud for time series. But if people who control Postgres themselves and run Postgres on EC2 instances or on GCP instances, doesn't matter, or on hardware, they can just use Timescale and be happy. But if for what to do for what happens if we use RDS? RDS doesn't provide Timescale. You build separate cloud, so split again, right?
Yeah. So I think two things. One is to remember, at its core, we are offering Timescale with Postgres. So it is absolutely the case that there are plenty of people who, when they use our cloud, some of them are using it really for time series workloads. They're actually also storing their relational workloads on it too. And so you could use our cloud for your traditional Postgres workloads itself. Now, if you don't have any time series workloads, we probably have. I mean, I think there's some great aspects of our cloud, but maybe it's less compelling. But I mean, this case of I'm on RDS Postgres. Timescale's not there. I think we've seen people who've taken those RDS Postgres workloads and actually have moved them to Timescale, and then they have their
questions like what extensions do you provide, additional extensions, because you're becoming.
I mean, there's a list. We offer.
Okay.
We have dozens of those extensions.
Okay. Interesting.
So a lot of the things which you want from a traditional managed Postgres, we offer as well.
Okay, another question. So you're building not sharding, but distributed system. Postgres doesn't have this. It's also lack of balance here. So Postgres itself needs something like this. You already pivoted from IoT platform to time series database. What about pivoting one more time from time series database to sharded Postgres or multi-node Postgres?
Yeah, so I think there's different, and this kind of goes to the specialization you talked about, and that like we're built on the same Postgres foundation, but we have built we have made decisions based on our use case to really optimize for that use case. And if you think about when you say sharded Postgres, I assume what you mean as a scale out like OLTP database. And so I think there's great.
Sorry, there are few solutions which are good if you need like analytical workload, but if you need sub-millisecond, for example, again, social media.
Yeah, I mean, I think there are definitely databases that are working on that. I mean, in the MySQL world, there's like out of YouTube, there's Vitesse. Obviously, in the not Cockroach,
Cockroach,
and their use cases like primarily geo-distributed OLTP. And so if you look at what they optimize for, it's actually different from what we optimize for. It's how to make a highly reliable running Paxos on everything for almost like a key value store. Yes, you can do SQL, but the workload isn't scan a million rows as part of a single transaction. It's an OLTP workload. So I think that if you squint hard enough, there are aspects of these architectures that look similar, but really they are making architectural design decisions based on what we need. And if you're going after the OLTP workload like Cockroach does, you're going to make different design decisions. And so I think that one general trend is that you kind of talked about something that Michael Stonebreaker wrote, is that developers are looking for best of breed solutions, right? And I think of Timescale as being that best of breed for time series or for kind of real-time analytics. We're not going after the same use cases as Cockroach would be.
So basically, many people are actually mixing that idea that just good scalable OLTP could be for analytics or just for OLTP. And the second approach is basically you provide fast OLTP to write the data, but the purpose is actually to make a good, proper analytics on that.
Yeah, I think, I think these things are continuums. They're not individual buckets. Yeah. And I think, engineers are also great of what I call doing off-label use. You like a technology.
That was actually my next question.
Start using it for different things, and it works well. And like we have people, using us for things that are really cool that we never thought of. But I think that you kind of look at almost that there's kind of spheres of things that technologies are good for. And where these spheres intersect, you see people adopting different technologies. And as you get more towards the extremes, it's more naturally let's say a Timescale workload versus a Cockroach workload or something.
We need to like wrap up soon and ask a few last questions. So very small question, what about licensing? I know there is Apache license, there is a Timescale license, and basically at some point not long ago you decided to provide all functionality to like open source and for free. But prohibit building clouds,
Yep.
right? It makes sense. And I know people like, for example, very simple example, there is Zalando Kubernetes operator. They also have Spilo project. It's like Postgres in container for clouds. And they provide only Apache version of Timescale, and they don't know what to do about it. Like I know like there are many requests because Apache version lacks some functionality, right? Like I'm very confused about this. Where to go to read about it?
Yeah, so I was intimately part of doing the licensing. I think long term, look, we I think we ultimately are we want our community to be able to be empowered to do as much as possible. We obviously view that the commercial approach that we're taking to take is to provide, a cloud platform. And so, effectively the concern that the challenge that ourselves and many other, software builders, Mongo, Confluent, Elastic, Redis, are all facing is that kind of the hyperscalers are at a unique position in controlling the market, so that they could, engage in, they have such market power that they could basically get use even when building a worse quality product. And so it becomes very hard for kind of independent software vendors to compete directly with people like Amazon, while you allow Amazon to run all of your software and you spend all this effort developing it. So what you see all of us trying to do is, how do we, on one hand, support the community and allow the community to take us in very different ways, and yet not effectively cripple our own ability to exist as a company by basically saying everything that we do, Amazon could use. And not only does Amazon get to send you a marketplace, but if you're a startup, Amazon has big enough cash, they give you $100,000 to use their stuff for free. Or if you're big enterprise customers, they lock you into a $10 million contract and get discounts so that your CFO says you could only use Amazon products, or charge 30% of marketplace. There's all these ways that they use their market power that makes it challenging to compete against. So, we obviously want to build a great product, but we kind of came to the conclusion that we need to make it such that if you want to manage service, really come to us for the best version of that. And so that's the approach we took. I think, the great thing is, some people say, like, why not just have an open core, closed source or an enterprise version? And that discussion is we always find confusing, because on one hand, we're saying all of our code's open, it's all on GitHub, anybody could do a PR to it, you could all inspect it. Unless you're running a managed cloud that is competing directly with us, like, you're free to use it for your own SaaS, for your internal use.
So I can include it to my own open source product.
Yeah, and so when people say, "Well, I wish you were only closed source," it's strange to us, because it's like we have. I mean, it's not a OSI license. We don't say that this is an open source license, but we've really tried to narrowly scope it, that says, unless you're basically like one of the cloud vendors who is competing directly with us by trying to offer TimescaleDB as a service, it's totally free to use. So for Zalando's case, Postgres just recently was really awesome. Actually, in the last couple of weeks, Postgres builds versions of the TSL, of the Timescale license version, our community version. And if you go to the, you could find a binary of our community, or a TSL license from the Postgres.org. So I think Zalando, I again don't know enough about the specifics, but as long as they didn't modify, there's a couple subtleties, but if they're just like building their own version, including it in their Docker,
it's about the Docker file, that's it.
Yeah, we have plenty of people who do that, and there's no reason why that. We allow you to distribute binary.
I think it's still up to their lawyers, but okay. Thank you for
it's pretty. Our license is meant. It was drafted with some of the really kind of best copyright and IP lawyers. So it should be relatively clear, but obviously there's. I
also have Docker files, so I think I can use it. Like, I can use a full version because I don't build cloud with Timescale, so I can use.
Yeah, you absolutely can use it.
Great.
Totally.
Great, but still, difference between Apache version and Timescale license version.
Yeah, so one important thing is we never relicense code. So everything that was in Apache stayed in Apache. We did not relicense any code. But back in 2018, we knew that this was knew that we were moving to the cloud. Knew that this was part of the strategy. Wanted to make everything free for people to use, other than this limited restrictions about don't run TimescaleDB as a service. So there are certain features. I think some of the great features: compression, continuous AGS, some advanced analytics, the automation policy, the multi-node. That stuff is community licensed as opposed to Apache 2 licensed.
Nice. Okay, not all questions asked, but we need to wrap up, I think. Yeah, maybe you have some last question.
I would say my question was answered before I was trying to ask them, so okay. I'm okay for now.
Okay, then I will ask. So imagine I
told you.
Yeah. Okay, I have very large database, for example, like 10 terabytes, maybe more, and I see Timescale fits very well for my needs, for my workload. I want to migrate, and I have a lot of transactions, 10K TPS or something, and maybe more. So I want to migrate without downtime. Should I write all procedures myself, or you have some tools for it? If you don't have, maybe you have plans to develop them for online migration.
Yeah, I don't think, I mean, we haven't really focused that much on live migrations of existing Postgres databases into Timescale. There is a migration because when you convert to a hypertable, it is moving the data inside your database because it has its own little format with all the chunks. That is done. It is done atomically. But yeah,
it's already implemented. Moving data between chunks, it's already implemented, or
no? I meant migrating from an existing relational data into Timescale.
Right.
It's it is atomic. It is done as a transaction.
Right.
But there's perhaps work we can do to support those type of live migrations.
Mm-hmm. Okay. I'm not going to ask more questions. Thank you so much. It was very, very interesting. I appreciate a lot.
Thank you. No, it's great. And to say, obviously we are, if I could, we're, I think, building cool stuff at Timescale, and obviously always looking to, we're continually growing and hiring. So if folks want to also love Postgres, work anywhere in the Postgres ecosystem, either, core database, writing our database, operating clouds, technical support, kind of Kubernetes, all the above, we're definitely looking. And if not that, we're also always open to contributions and either code, docs, or just part of the active communities. That'd be great.
If this, I need to ask one more question. How many engineers do you have right now?
Engineers, I think engineering is around 40 between some different teams, but growing quickly.
Distributed, right?
Highly distributed. We're in 20 countries right now and 6 continents.
Distributed, reliable, and so on. Okay.
There you go.
Good. Thank you, Mike.
Like the database.
I enjoyed it. Thank you so much. Thank you everyone. Don't forget to subscribe and like this video to support our small channel.
I think you're supposed to say smash the subscribe button. I think that's what you
smash it. Big like and so on.